Well, thanks for coming to the problem session, guys. Hopefully we can get a little practice in here. I know it's been a little while since we have been doing this stuff together, so hopefully we'll get a little practice going. There's, as you know, a test coming up on Wednesday and a homework assignment due on Monday. I will have the solutions to that assignment up by Monday night, so you'll have everything available to you. What we're going to do in this problem session is several problems that are related to the more recent material. Figured that would be the best thing to focus on at this point, and then that'll hopefully help get us back on track. And then you can look back to the, I guess, problem session 5. I just did the video by myself before the break, and then even back, I think, problem sessions 4 and maybe even 3 are also relevant for this upcoming test as well. You just have to double check the dates and what the topics are, because this test will start with sections 4.4 and 4.5. Right, so the test covers 4.4, 4.5, and then 5.1, 5.2, and 5.3, and then 6.1. And 6.1 is the more recent material. We're going to spend a lot of our time today talking about that recent section that we kind of covered last Wednesday before the break. So I have a variety of problems here to practice all of this stuff. Okay? Any questions about the overview of what we're going to do? Yeah, the best way to sort of get comfortable with this material is to just practice as many problems as we can. Don't forget to do the sample test as well. It's going to give you even more practice. So this is good. So let's start off with problem number 1. This is problem session number 6, by the way. And this is the first problem. Okay, so I'm just going to abbreviate the question up here. We have the problems in front of us, but we're going to take two numbers, a less than b, in the real numbers, and we're going to assume that f is differentiable on R. Okay, so if it's differentiable on R, then remember that it's also continuous on R. That's one of the many theorems that are in the review packet that you should make sure you know the statement and the proof of that. Any of those items that have a double star on them in the review packet, please know the proof. There's a good chance I'll ask you one of those, or I might give you a choice to prove 1 out of 2 or something like that. So anyway, this fact that a differentiable function is continuous is certainly in your review packet. Okay, so then what we're going to do is prove that there exists a C in the open interval AB such that f prime of C is equal to f of B e to the sine B minus f of A e to the sine A all over B minus A e to the sine C minus f of C times cosine of C. So this is quite a complex expression here. We're not asked to figure out what C is, we're just showing that this C exists. Okay? So you have to look at a question like this and think a little bit about where does it fall in the material. Now, we didn't learn about differentiable functions until chapter 5. So assuming f is differentiable and looking at an equation that involves the derivative of f must be something from chapter 5. It's not chapter 6 either, because chapter 6 is about integrals. This has nothing to do with integration. So this is a problem in chapter 5, and you're showing the existence of a C such that f prime of C is equal to something. What does that remind you of?
The mean value theorem.
Exactly, the mean value theorem. For the mean value theorem, you have an interval from A to B, right? F has to be continuous, if you remember the assumption, has to be continuous on the closed interval AB and differentiable on the open interval AB. But see, look, F is differentiable everywhere, right? So I don't care what the interval is, it's going to be differentiable and continuous on AB, whether you look at it as open or closed. Okay, so given those assumptions, then the mean value theorem says that there exists a C. Okay, good. We're trying to prove that there exists a C in the open interval AB such that the mean value theorem says this. Right? This is the mean value theorem, which is obviously not what we're being asked to show here. Right? So what is actually going on here, do you think?
Would you define G? A function G?
Exactly. What we're going to be doing on this problem, guys, is we're going to apply the mean value theorem, but not straight away to f itself. We're going to apply it to another function that we have to create. Now, this new function, whatever it is, needs to still be differentiable on the interval that we're looking at. And how are we going to come up with that new function? You have to look at the form of what you see right here. Yes, question?
So to you, what gives away that we need to construct the function for this particular example? So what's the telltale sign for you to say, oh, we need this function instead of f?
Well, I know that we cannot, I know that if we try to apply the mean value theorem directly to f, all we're going to get is what I just erased,
Right.
which is this, right? This is not what we are hoping to achieve. That's the reason. So if we apply the mean value theorem to f, we're going to get this, which is not what we're looking for. So we need to think about creating another function g, and really the hardest part of a problem like this is just coming up with the function that you should work with. So you have to look at the form of this and ask yourself whether there's a reasonable candidate for a function that you could define. Does anybody want to throw out a guess?
It's something multiplied by e to the sine x.
Okay,
Maybe
so
f of
e
x.
to the sine x, pardon me?
F of
Yeah,
x.
how about just f of x times e to the sine of x,
Okay.
right? Now, these functions are, so sine of x is differentiable. We proved in one of the earlier problem classes that it has a derivative equal to the cosine. E is also a differentiable function. This is a composition of differentiable functions. They're differentiable on all of r. So e to the sine x is differentiable on all of r. And now I'm taking the product of two functions that are both differentiable on all of r. So I can just apply the product rule to take that derivative, right? Okay, so let's just note here that g is differentiable on r, being that it is a product and composition of differentiable functions. So what we can do is we can apply the mean value theorem to the function g. Okay? So what is that going to say then? That's going to say, thus, there exists a c in, we already have this interval a to b established, right? So there exists a c in that open interval such that g prime of c is equal to g of b minus g of a all over b minus a. Agreed? And of course we can plug in, we know what g of b is. G of b is just f of b e to the sine b, and then g of a is f of a e to the sine a, and this is all over b minus a. Okay? Does that make sense? And you can kind of see part of that expression in the formula you're trying to prove. Now we have this part over here that's subtracted off. That looks a little funny. Obviously we have g prime of c rather than f prime of c. So what am I going to do to get this to work out the way I want it to?
Get the derivative of g of x.
Exactly. We have a formula here for g prime. But in order to really know what is g prime of c, I have to differentiate g to get that. Okay, so let's use the product rule. See, this is a nice question because it is using the more than one idea here, right? So using the product rule, actually it's the product and the chain rule. Product and chain rules, right? So g prime of x is equal to, so it's the first one, which is f of x, times the derivative of e to the sine x. What's the derivative of e to the sine x?
It's e to the sine x times cosine x.
Exactly, e to the sine x times cosine of x, right? Okay, and then plus the derivative of f, so that's f prime of x, times the second term, which is e to the sine x. So there you go. Okay? Now what we can do is we can plug in c Right, that's what you would want to do, because look over here, you have an expression for g prime of c. So g prime of c is just, of course, f of c, e to the sine c times cosine of c, plus f prime of c times e to the sine c. So just everywhere you see an x, we can just put in c instead. And all of that, right, all of that has to equal the right-hand side here, right? Okay, so we have f of c times e to the sine c times cosine of c plus f prime of c times e to the sine c equals what we have over here on the right-hand side of the bottom line here, f of b e to the sine b minus f of a e to the sine a, all over b minus a. Okay. Now, at this point, the trick is to just solve for f prime of c. Okay. Now solve for f prime of c. That's just a very, very simple little algebra manipulation. I'm not going to take the time to do it. You can almost see it in your head what's going to happen. You're going to get exactly the box. You're going to get exactly the formula in the box over there. Right? So I'll leave that part out. The main thing I want you guys to be able to do is recognize from the problem how you're going to approach it. How you're going to approach it. So you have to look at this question and say, okay, this is a very complicated formula, but it does kind of remind me of the mean value theorem. It's just I have to apply it to a tweaked function, not to f, but to g. Coming up with what g should be is obviously one important step. And beyond that, it's pretty simple. You guys can make these problems up and practice them. Like you can start by figuring out what you're going to choose g of x to be. Like, so for example, just to give you an example, what if you just did this? Okay, you could just, let's say you and a friend get together and you trade problems. So you could do something like that. You make this up, you could go through the motions of taking the derivative of g, right, and getting it in terms of f. So you'd solve it out for f prime of c, right, and then you would give your friend the formula for f prime of c and say, how do you prove this? Okay. And then they could give one to you as well. So there's a million ways to create nice little problems that involve variations on that basic mean value theorem. Is everybody okay with that example? Okay. You feel like you would recognize that kind of problem if you saw another one like that? Yeah. Okay, great. All right, so just wanted to do that to kind of get started here. Okay, let's go on. Actually, let's go on to the very last problem next, because then all the other problems will be about integration. So if we just do the very last problem, then we'll be done with everything except the chapter 6 stuff. So let's look at number 8, the very last problem on the sheet. This is a problem where we have a function from r to r, and the formula is f of x equals absolute value of sine of x. Okay? And then the question is going to ask us several things here. Is f continuous on r? Uniformly continuous on r? Differentiable on r? And Riemann integrable on r? Okay, so these are the 4 parts. So let's just do this one next, because once we've done this, we'll be in pretty good shape for everything else. Oh, and yeah, okay. Yeah, sounds good. Okay. Guys, all right? There are relationships between these, right? So, for example, if f is differentiable, then it has to be continuous. If f is uniformly continuous, it has to be continuous, right? So, If it's not continuous, then none of the first three can be true. All right, so we know something. We don't really have to answer this like it's 4 separate problems necessarily. Okay. Before we actually solve the question, it might be helpful to draw a picture of this function. Just draw a little graph maybe. Unless you guys think you know the answers already. Let's just draw a graph. Let's draw a graph and see, because it's not necessarily totally obvious. So the graph of sine of x, this is just sine of x right here. So if we take the absolute value of the sine of x graph, right, then basically we're going to start off, we're going to get a bunch of humps that are like this, it looks like, right? Goes in both directions. Something like that. Okay, so we have that. And so based on this picture, do you believe that this function will be continuous on R?
Yes.
I mean, the idea there is, well, can you draw the graph without picking up your pencil? And, well, it's pretty clear that you can. Okay. So the idea is probably this is going to be yes right here. Okay. Uniform continuity. So do you think this function is going to be uniformly continuous on R?
No.
Don't think so?
Because it has those sharp points when it's going down.
Okay.
When it intersects the x-axis. That's my reasoning.
So how steep is the graph at those sharp points? Is it going in vertical or is it going in at an angle?
It's not too steep.
Cosine, right? Because of derivative.
Okay, the derivative of sine is cosine, right? And so that's the slope, right? The slope of this graph would be given by the cosine graph, and that means that slope is always between -1 and +1. Do we have anything about slope that relates to uniform continuity?
Yeah, if a function has a bounded slope, then it's uniformly continuous.
Okay, if the function has a bounded derivative on an interval, then it would be uniformly continuous on that interval. Now, but there's a problem here. So that's getting ahead of ourselves, because to use that criterion, we have to have a differentiable function. So let's actually talk about the third question first. Is this function going to be differentiable
Yes.
on every single point of R? Just intuitively, would it be?
Except at those points.
Right at these points, right? There's a sharp corner there, right? Remember, differentiable just means it has a slope, right? Does this graph have a slope right here? It's not a well-defined slope, right? There's sort of a slope from one side and a slope from the other side, and they don't agree, right? So this function actually is not going to be differentiable on R. We're going to come back and prove all of these assertions in a minute. I just want to get the intuition down before we go any further. So this throws a wrench in things, because we wanted to use the bounded slope idea as that was, I think it's corollary 5.4. If f has a bounded derivative, then f is uniformly continuous on whatever the domain is. So I guess you could say that the function is uniformly continuous everywhere except the endpoints of each of those humps. But you're asking about uniform continuity on R. Still, however, right, the slope is well-defined and is bounded at almost every point of the real number line. It's just these points right here where that's failing. And we do know that the slope, as the graph comes in towards that dot, that slope is less than or equal to 1. So it is kind of, it really intuitively it should be uniformly continuous, for the same reason that if the function did have a derivative everywhere and it was bounded everywhere, that we would use this corollary to say that it was uniformly continuous. Somehow that shouldn't change just because there's these isolated points where the derivative fails to exist. So intuitively, does it seem reasonable to say yes on this? Should be uniformly continuous? Let's try it. We'll see it. We'll see in a second. Okay, and I also realized I have a typo in my questions and in my solutions here. Riemann integrability, I mean, I could ask you if it's Riemann integrable on all of R, but based on just the material we have learned so far, I want to change this and make it a little bit easier. So I will fix this in my handout. It should be the closed interval from 0 to 1. That's really what I want to say. So this is pi over 2 right here, so 1 is like right there. So we're talking about on this interval here. Do you think you're going to be able to do this integral? Calculate that integral probably?
Yeah.
Yes.
Yeah. I mean, there's going to be a theorem that says any continuous function is Riemann integrable. So that once you've said yes here, then this is also yes. We don't know that theorem quite yet, but it is true. And we'll argue in a moment why we can, even without that continuity theorem, we can say yes there. So these are the right answers. These are all the right answers. What we need to do is try and prove them now. Okay? We need to try to prove them. Do you think it's going to be worth our time to prove that f is continuous on R? Well, look, as soon as we get done doing that, we're going to have to prove that it's uniformly continuous on R. Remember that any function that's uniformly continuous on a domain D is continuous on that same domain. So why not just start here? If we can prove this one, we get this one for free. Right? So let's prove this one. Okay? So I'm going to prove that f is uniformly continuous on R. And I'm not going to use the bounded derivative criteria because, as we've said already, that derivative doesn't exist everywhere. If it did, then I might want to use that, but it doesn't. Okay? So in order to prove uniform continuity, if we're not using the derivative at all, what are we going to use? The definition, the epsilon delta definition. Exactly. So let's see, how is that going to start off? That's going to be, let epsilon greater than 0 be given. Okay, and then we're going to have to come up with a delta, right, at some point here. Oh, by the way, if you did want to just prove continuity directly, it would be very straightforward because this function f is a composition of two continuous functions, right? Namely sine of x and absolute value of x. So you could always argue it that way as well. So, okay. So if we look at, maybe we just need a little bit of scratch work. What we're gonna basically do is we need to find a delta greater than 0, right? Such that if absolute x minus y is less than delta, then absolute f of x minus f of y is less than epsilon. This is the usual definition that we have to work with. So it might be helpful to examine this criteria here that we're trying to prove, right? Absolute fx minus fy less than epsilon. So just by way of scratch, if we look at that, so absolute of f of x minus f of y, right, being less than epsilon. Guys, when you're doing these steps, if you're going to use the scratch work and tell me to retrace the steps of the scratch work, make sure your scratch work is cleaned up then. You can't give me really scratchy scratch work and then use it in your proof. Okay? It has to be very nice. So in this case, I'm going to just replace f of x with absolute sine x minus absolute sine y less than epsilon. Okay. Now this looks like something we may have seen before. We're taking the absolute value of the difference of two absolute values. So this takes us way back to a corollary, I think it's corollary 2.1, which says that this is less than or equal to the absolute value of a minus b. So in other words, if this one is less than epsilon, then definitely this one will be less than epsilon. So what I can do is I can do a backward arrow, only backwards here, that says absolute sine x minus sine y less than epsilon. Okay, does that make sense? So this is going to be by corollary 2.1. I know it goes back a little ways, but just hopefully it looks a little bit familiar. Now this one, this just looks like the condition for the functions f of x equals sine of x. And that function is continuous. In fact, it's differentiable. We proved that. So because, okay, so I think we have a strategy for our proof now. Given the epsilon, the fact that sine of x is continuous means that we can already find a delta, right? So you could imagine fixing the point y and letting x vary and just use the ordinary continuity definition for sine of x, right? To prove that basically as long as absolute x minus y is less than delta, then absolute sine x minus sine y is less than epsilon. In other words, I think we can get this. We can get this one, and therefore this one, and therefore this one. Let's try and write down the full proof. I'm not just going to wave my hands about the scratch work. Let's actually write the whole thing out. Okay, so this is the last thing we wrote. Let epsilon greater than 0 be given. So let's do this. Since sine of x is continuous everywhere, so it's continuous on R, okay, then given any y in the real numbers, so take any point, the y is like the c in the definition of continuity, right? Okay, then there exists a delta greater than 0 such that if the absolute value of x minus y is less than delta, then the absolute value of sine of x minus sine of y is less than epsilon. Is everybody okay with that? See, I'm using ordinary continuity here. That's why when you have ordinary continuity, you imagine fixing a c, and then you choose a neighborhood of x's that are close to c. But the c is really just the y. Right? So given any y, I can find a delta such that as long as x minus y is less than that delta, then sine x minus sine y is less than epsilon. Great. And now, by corollary 2.1, we'll just write down all of the scratch work backwards. Absolute value of absolute sine x minus absolute sine y, that's less than epsilon. Okay, and so absolute fx minus fy is less than epsilon as needed. Okay? That seem all right, guys?
So that same delta that made sine of x continuous also works for the uniformly continuous?
Yeah, that's the thing about it. We just have a single delta that works at all points of the real number line. Exactly. You just need one single delta. Exactly. Okay. Pretty nice. Pretty simple argument. Or you could just use the fact, here we didn't use the strongest thing we could use. So we could have said sine of x is uniformly continuous on R. Now why is that?
It's bounded.
Because what's bounded?
The derivative.
Right, this function is differentiable, right? So if you take off the absolute value bars and you just look at this function alone, we could have actually just said uniformly continuous here. I could have made a stronger assumption. Well then, I wouldn't have to even worry about whether I'm fixing y or fixing x. Then I would just take any 2 points x and y that are less than delta apart. That delta would have to exist because sine of x is uniformly continuous on R. So you can find this delta, and as long as absolute x minus y is less than delta, then this would have to be true. So that actually would be an even slicker way to justify it. Just use the uniform continuity of the sine function. Okay? Does that make sense, guys? So it's uniformly continuous on R, which means it's continuous